Our next topic is effectiveness method, and it is also known as NTU method. It is very simple to use LMTD method of heat exchanger analysis. When it is easy, it is very simple. When temperature, inlet and outlet temperature, mass flow rate of hot and cold fluids and overall heat transfer coefficients are available. If U is available, temperatures inlet and outlet they are available, mass flow rate MC cold fluid, MH hot fluid temperatures, mass flow rates are available, then we can easily do the analysis with the help of log mean temperature difference method. The heat transfer surface area and size of the heat exchanger can be calculated. We can calculate then area, or we can say the size of heat exchanger. There are four main temperatures: temperature to hot fluid temperature, inlet temperature of hot fluid, outlet temperature of hot fluid. Two temperatures are related to cold fluid temperature. For a counterflow heat exchanger, this is the inlet temperature of hot fluid, this is the outlet temperature of hot fluid. If the type and size of the heat exchangers are specified and the mass flow rate for the prescribed mass flow rate, only inlet temperature of both fluids are known. If we know only inlet temperature TCI and THO of both the fluid, then the use of this method, which is a LMTD method, becomes helpless. It is very difficult. If it is used in such a case, then the procedure would require very tedious iterations. So to overcome this problem, when that all temperatures are not available, there is another method. We know that method. The name of that method is effectiveness method or NTU method. Effectiveness method and NTU method. In this method, the term NTU, which is known as, or we can say there is another term effectiveness, which is represented by epsilon. It is a dimensionless parameter. Effectiveness is a dimensionless parameter. It is the ratio of actual heat transfer to the maximum possible heat transfer. If we assume Q divided by Q max, Q ACT actual divided by Q max. Heat exchanger effectiveness, Q actual divided by Q max. Actual heat transfer of any heat exchanger can be represented with the help of hot fluid temperature difference and with the help of cold fluid temperature difference. If we are using the cold fluid, TCO, TCI are the two temperatures of the cold fluid, and M and CP, MC and CPC are the cold fluid mass and specific heat, and divided by Q maximum. Similarly, we can write the equation for effectiveness of heat exchanger in terms of hot fluid. In this case, we have used the temperature difference in the form of hot fluid temperature, THI and THO. The actual heat transfer rate in the heat exchanger can be determined, actual heat transfer rate, from the energy balance on hot fluid and the cold fluid. Let Q be the actual heat transfer. Let's say this Q is the actual heat transfer. It is represented by Q. For the cold fluid, it is in the form of cold fluid temperature. This cold fluid will get heat from the hot fluid. Heat lost by the hot fluid will be in the form of hot fluid temperature. In this case, these are the two another parameters, C, capital CC and CH. These are the specific heat of the cold fluid. Cc is the specific heat of the cold fluid, and Ch is the heat capacity of hot fluid. It is C, capital Cc is equal to multiplication of Mc Cpc, and capital Ch is a product of Mh Cph. In the definition of heat exchanger, there is a ratio of actual heat transfer to the maximum possible heat transfer. We can write the equation for actual heat transfer, but what will be the equation for maximum possible heat transfer? Maximum possible heat transfer will depend upon the maximum temperature difference, delta T max. In the system, there are 4 main temperature, 2 hot fluid temperature and 2 cold fluid temperature. In overall system, what is the maximum temperature? It is Thi. It is maximum. What will be minimum temperature? Overall minimum temperature is here, Tci, cold fluid temperature. Then we can say the delta T max, maximum temperature difference, will be the difference of these two temperature, Thi and Tci. Then we are interested to find the maximum heat transfer, which depends upon maximum temperature difference. Again, heat is equal to mCp delta T. M multiplied by Cp is represented by capacity. Delta T is the maximum temperature difference, T max, and C will be C minimum. C minimum may be of cold value, it may be of hot, it may be of cold fluid, and it may be of hot fluid. Either of the fluid or hot or cold, depending upon the product of mass flow rate and the specific heat. Then effectiveness, which is the main parameter we are interested for the cold fluid and for the hot fluid. First, for the cold fluid will be in the form of ratio of these two equations, actual heat transfer to the maximum possible heat transfer. Maximum possible heat transfer, we have put the value of maximum heat transfer into the equation of effectiveness. This will take the form of this equation, which is in the form of hot fluid temperature. It is in the form of hot fluid temperature. For hot fluid temperature, this is again the equation in the form of hot fluid temperature. It is the actual heat transfer. This is the maximum possible heat transfer. And effectiveness is the ratio of these two quantities. Or when we can say Q, which is the actual heat transfer, will be a multiplication of effectiveness multiplied by maximum possible heat transfer. It is a just rearrangement of above equation. Then I'm going to introduce NTU, number of transfer unit. It is known as number of transfer units. Number of transfer unit. By definition, it is equal to UA upon C minimum, overall heat transfer coefficient, area through which the heat will exchange, divided by heat capacity of out of 2, which is minimum, UA upon C minimum. And as from this relation we can see NTU is directly proportional to overall heat transfer, directly proportional to area. From the geometrical parameter, it is directly proportional to area. And when you the overall heat transfer U and area of the heat, what is the physical significance of NTU? And when NTU is directly proportional to A, therefore NTU is the measure of physical size. It is the measure of size, physical size, or you can say heat transfer area of the heat exchanger. Higher the value of NTU, larger will be the area, or we can say the physical size. Then there is another term which is also required for this analysis, that is a capacity ratio. Capacity ratio is nothing, it is a ratio of two capacities, minimum fluid capacity, maximum fluid capacity, or you can say MCP divided by MCP. One is of minimum and second is of maximum. We can also conclude effectiveness is a function, it depends upon number of transfer unit NTU and capital C, which is a ratio, capacity ratio. Effectiveness of a parallel flow heat exchanger. Now we will apply this method for parallel flow heat exchanger. Effectiveness of a parallel flow heat exchanger. We are interested to derive the relation for parallel flow heat exchanger by using the NTU method or effectiveness method. We already know for the parallel flow heat exchanger, by using this temperature distribution over the heat exchanger along the length, we have assumed an elemental strip of having area dA. This is the inner side. Here temperature will be Thi, Tci, Tho, Tco. For a parallel flow, the direction of both fluid will be in the same direction. We will assume here the temperature difference delta T. By this analysis, which we have already done for the case of LMTD, by using the same diagram and same method, we already know for a double pipe heat exchanger, parallel flow heat exchanger, we already know this equation. Okay. Where delta T2 and delta T1, delta T2 and delta T1, delta T1 and delta T2, these are the temperature difference. We will put the value and integrate this equation and simplify it. By rearranging, equation will take the form of this equation. Finally, we will solve this equation for effectiveness, which is for the parallel flow heat exchanger. By solving this equation after rearranging, it will take the form of parallel flow heat exchanger. It will take the equation for parallel flow heat exchanger, effectiveness of parallel flow heat exchanger. Again, this is the equation which is in the form of final equation, which is in the form of NTU, number of transfer units, C capacity ratio. In the similar method, by following this procedure, we can derive the relation for effectiveness of heat exchanger for counter flow heat exchanger. In that case, the temperature distribution diagram will be different, will be for the case of counter flow, and we will solve the equation in the similar, will derive the relation in the similar method as we have done for the parallel flow heat exchanger. In the case of counter flow heat exchanger, our final result, it will be in the form of in case of counter flow heat exchanger, counter flow equation will be in the form of 1 minus exp minus NTU 1 minus C divided by 1 minus C exp minus NTU. Final equation will take the form of like this. Next, we have to solve the numericals for a heat exchanger. There will be some methodology, you have to follow some methodology to solve the numerical. For rating and sizing, if we are interested to find the size area of the heat exchanger, then we will follow methodology. There will be few steps. The first step will be calculate capital C, which is the capacity ratio of C minimum by C maximum. Then calculate NTU. If UA C minimums are available, find out NTU. By this methodology, we need effectiveness, which is a epsilon. From the chart, we can note down the value of epsilon. Then calculate Q. We know this equation. Calculate Q. Then calculate outlet temperature. These are the steps to find the size of the heat exchanger. Then to find the area and length. To find the area and length of the heat exchanger, calculate actual heat transfer in the form of cold fluid temperature, hot fluid temperature. Calculate U. If we are interested to find the U, which also depends upon convective heat transfer coefficient on inner side and convective heat transfer coefficient on outer side. If they are not given, sometimes they are not given, sometimes they are given. If they are not given, then we have to find the Reynolds number. We have to follow that procedure. We have to decide whether the flow is turbulent or laminar. Let's say for the case of turbulent, Re is greater than 2300. For the case of turbulent, Reynolds number value is more than 2300. It means it is a turbulent flow, and we will use heat transfer equation in the form of Reynolds number, Prandtl number, and Nusselt number. And in that case, with this parameter D, which is a characteristics diameter, it will depend upon area, and perimeter P is the perimeter. Then calculate LMTD, which will depend upon temperatures. Next step will be the calculate outer area from this equation. From area we can calculate the length of heat exchanger. There is another method which is also applicable, that is also known as alternative method. For that calculation, first we have to compute C minimum by C maximum with temperatures, calculate effectiveness. In this case temperatures are given and we will calculate effectiveness. But in this method, in this alternate method, NTU is taken from the chart. In the previous method, and effectiveness was taken from the chart, but in this method, which is the alternative method to solve the numerical, we will note down the value of NTU from the chart. Then we will calculate area and length.